Welcome to week 4, ISDA 609. So this week we're going to cover simulation. Simulation has a couple of aspects. One is how to simulate this deterministic model behavior, and the second one is how to simulate probabilistic behavior. In between, we have to learn how to generate random numbers so that we can simulate probabilistic behavior. Inventory model and queuing models are classic examples of using simulation modeling. So there are a couple of possibilities that when we need simulation. One possibility is we're not able to construct an analytical model that can adequately explain the behavior observed. And also, in some cases, we don't have enough real data. We have to use simulation or experiment to obtain more data. And in the case that the alternative procedures need to be tested does not exist, we have to use simulation to validate the real world or validate the model. And the behavior could be deterministic, model could be deterministic or probabilistic as well. So this is an example of using simulation. So in the case that if we have a point P here, when the P is under the curve, if we have enough points under the curve and some points above the curve, we could be using the number of points counted below the curve divided by the total number of random points to approximate the area that is under this particular curve. As you can imagine, if we only have 20 points that we sampled, then we probably would be very difficult for us to have a solid approximation of the area. If we have 20,000 or more data points, most probably we could simulate the area very well. So when it is below this curve, we can't it's below, or when it could be the next point, it could land up here, and then we count it as a total number of points, but we don't count it as the number of points below the curve. So very good example here. And how to simulate the volume on the curve, very similar to what we just discussed, using the number of points counted below surface in first octant divided by the total number of points that were sampled. How to generate random numbers. So one of the methods is called middle square method. So we can start with a 4-digit number x0 called the seed. Important concept, seed. And then square it to obtain a 8-digit number. Add a leading 0 if you only have 7. And then we could we take the middle 4 digits as the next random number, so on and so forth, so that we get a number. For example, we can use it as 1, 2, 3, 4, and then square it, and then take the middle 4, and so on and so forth. The other method that very popular is called linear congruence. That is to say, use xn plus 1 equals to a times xn plus b mod c, where c is a modulus, a is a multiplier, a is called a multiplier, and b is an increment. So very important is to pay attention to the possibility of cycling, and also it could be lack of statistical independence among the numbers in the list of random numbers. So fitting probabilistic behavior, three simple probabilistic models. One is flip a fair coin, The other one is roll a fair die and also roll an unfair die or pair of unfair dice. These are some examples in textbook. Please read. So here is a fair coin example. So essentially, it's just whether you get it head or tail. If obtain a random number between 0 and 1, if it's between 0 to 0.1, we could count it as a head, and so on and so forth. Use a total number of counter that's in this range area divided by the total total flips, so that we can get the probability of head. And a fair dice, if it's between 0 and 1/6, counter 1 will be incremented 1. Counter 2, in different cases, different counter would be incremented. And then at the end, we could use different counter divided by the total number of rows. And also an unfair die. So essentially saying that between different area, the possibility is different. For example, this particular range has covered 0.2 to 0.4, but here only the difference is only 0.1. Here the difference is 0.2, and here the difference is even 0.3. So different area have different possibility. So in the textbook, there's a inventory model. So average daily cost is a function of storage costs, delivery costs, and demand rate. So pay attention to that. Some of assumptions for simulation models may be results from analytical models, meaning we can use a combination of simulation and analytical methods together. Here is an example for the inventory model. As we can see here, we have an initialization, and then we try to look at the cost and the inventory, and here are the detailed steps on how to generate random numbers, how to update the current inventory, and how to go to step 2, go back, and back and forth. At the end, we can calculate the average daily cost. And a queuing model. A queuing model is a very important application in some cases, like the harbor system could be the Walmart supermarket, when they want to make a decision on how many servers they need, how many checkout stations the system might need. So some other examples: morning rush hour for queuing models, and multi-server queues. Yeah, we discussed this just now. So these are the homework for chapter 5. Thank you.